can start.
Okay, so hi everyone. My name is Fiskani Kondowe, and I just want to give a basic background on statistics, basically the methods that Moses would want to showcase in R later on. I hope I will be able to finish earlier, but if not, then probably the analysis will be done next week. So I've just called this particular session Basic Statistics for Non-Statisticians. I've just picked only the things that I think are relevant. We are going to talk about chi-square tests, t-tests, and tests for correlation. That's what we'll talk about, and what it means when you get the results that you get when you do analysis on a real life data set. If there are any questions, then you just type them in the comments section, and messages. All right. Oh, for some reason my slideshow is not moving. Okay, yeah. So for statistics, basically when we're using statistical methods, we're just trying to get information from raw data, and we're using different methods that are there. In two broad categories that you talk about most of the times is you're either doing descriptive statistics or inferential statistics. And what you have been doing basically is descriptive statistics, where all you're trying to do is to describe the data, have a picture of how the data is like. And in there, you are talking about constructing graphs, bar graphs, histograms. All of those are two-way tables, one-way frequency tables that you have been constructing in the past couple of weeks. And all you're trying to do is to see how your data is like. So you want to see how many in the data set were females, and how many were males, and how many females, for example, were in a particular job category, how many males were in a particular job category. So there you're doing descriptive statistics. It's what you do most of the times when you just get your data, and then after that, you want to go into inferential statistics. And in inferential statistics, you would think of it like you're digging deeper into the data. You want to find relationships in the data, associations in the data, things that are not just describing the data per se. Now you're moving into inferential statistics. So I wanted us, before we go into the analysis that we want to look at, to talk about these particular aspects or this particular notation. So when you're looking at data, you're either talking about continuous or categorical data. Continuous data, it is the data that can be collected on a continuous scale, or a characteristic that has values that can be measured on a continuous scale. What do I mean by that? I mean the values, that particular characteristic variable can take on any value. Okay, so you're looking at variables like age, you're looking at variables like weight, height, amount of fuel that you put into a car, or you're looking at temperature. So it means you can have 10 sampling units in your sample, and everyone will have their own height. One would be 1.57, the next one 1.56, another one 2 meters, and so on and so forth. So that's a continuous scale. On the other hand, in categorical data, it is where all the sampling units are falling into predefined categories. So it means if you have a sample, for purposes of this particular session, we are going to look at gender as just being male and female. So it's either a person is male or they are female, if your sampling units are people. And for also purposes of this session, when I talk about sampling units, I'll be talking about people, but it doesn't always have to be people. It could be cars, it could be trees, it could be plants, it could be anything. So in categorical data or categorical variables, it is where every sampling unit is falling into a predefined category of the variable. So it's very important to know which variable you're dealing with, if it's continuous or categorical, because that will also determine the type of analysis that you will use. Moving on, you look at parametric or non-parametric statistics or tests. In parametric tests, these are tests that you use when the distribution of your data is known. So in statistics, data will follow a particular distribution. You have a lot of distributions like the normal distribution, the gamma distribution, the Poisson distribution, exponential. So if the distribution of your data is known, you're going to be using parametric tests. If it is not known, you are going to use non-parametric tests. So to say, for most parametric tests, they are non-parametric alternatives for those tests. But for this particular session, this is not our focus, but then I will just mention which tests are parametric and which ones are parametrics and non-parametrics among the ones that we'll be looking at. So don't be surprised if you come across this. Just know that if you are talking about a parametric test, it means you know the distribution of your data. Well, as a non-parametric test, and it means you do not really know the distribution of the data, or it doesn't follow any particular distribution in the tests we change. The more comprehensive ones and advised are the parametric tests, but then you realize that, in a case where you don't know the distribution, it means that you compromise. Now you go ahead and use the non-parametric test, and you have to tell us or tell whoever it is you're reporting to what type of tests you have used. Okay, so all right, so the test that we're going to look at for this particular session, we're going to look at the chi-square test, which is the only non-parametric test in this session. And then we'll look at the Pearson correlation test. And then thirdly, we'll look at the t-test, or they're called student t-tests. And then 3 categories: the one sample t-test, independent samples t-test, and dependent samples t-test. So it has to be 2 independent samples and 2 dependent samples t-tests. And finally, the analysis of variance. Now, all of these tests that we have here, they also have their non-parametric equivalents, which we are not going to look at for this particular session, but they're there. The Kruskal-Wallis, you find them there. They are the alternatives for these particular parametric tests. Now, in testing, whatever research that you are doing, you have a claim or something that you're trying to test or to look at. So a hypothesis is just a claim about a population characteristic or parameter. You realize that in a population, the variables you're looking at, they have parameters. And most of the times we're using a sample to estimate those particular parameters. And in hypothesis testing, we are trying to test a claim that has been made about a population characteristic. And you'll find that we'll be talking about defining a null hypothesis and an alternative hypothesis. Don't worry about it. The alternative hypothesis is just the opposite of the null hypothesis. And for the particular test that we're going to be looking at, I will just tell you how the hypotheses are defined for those tests. I'll not go into how the reasoning behind it, as I don't think that is necessary for this particular session. But if you still want to know, then you can talk to me privately and I can explain that to you. Now, when you're doing tests, you'll find that most of the times you find people are making a decision based on a p-value that they see on the results that they get, okay? And then most of the times we are comparing this p-value to an alpha value. There is an A here, but it's supposed to be an alpha as a symbol. I don't know how why I have an A here, but anyway, it doesn't really matter. It's just notation. So we are saying that from the study that you conduct, the sample that you generate, when you do the analysis, you get a p-value that is attached to those results. And how do you make a decision on the null hypothesis? You compare the p-value that you get to a fixed value, an alpha. And the decision rule is that you reject the null hypothesis if the p-value from the sample, okay, is less than your alpha. Now, the alpha is also called the significance level, and it is a fixed probability, okay? And most of the times you find that an alpha, the default alpha most of the time is an alpha of 0.05. So it's a fixed probability. You fix this probability at the beginning of your study. If you read the books, you find that this alpha value, this significance level, has a definition that sounds statistical. But for the purposes of this session, I will just tell you in simple layman's terms what probably you're talking about. What you are saying is that if you fix an alpha before you do a study, say alpha is equal to 0.05, it means that is 5%, yeah? If you convert that to percentage, it is 5%. What you are saying is that you are only okay making the wrong decision 5% of the time. What wrong decision is that? The wrong decision of rejecting the null hypothesis when it is true. So what you are saying is that every analysis that you do, as long as the boundary for making a decision is 5%, you are comfortable making that decision of rejecting the null hypothesis. Otherwise, if the probability calculated from the sample is greater than what you are comfortable with, you are not going to risk rejecting the null hypothesis, because it means now there is a higher chance that that is a mistake. And what is that probability that we are talking about? It is this p-value, the one that you are comparing to the alpha. So what it means is that if I conduct a study and I get a p-value of 0.04, what it means is that there's a 4% chance that my decision of rejecting the null hypothesis is wrong. And since I fixed that I am okay with 5%, then it means I can go ahead and reject the null hypothesis, okay? But if the p-value turns out to be higher, and say 7%, it will be out of my comfort zone, so I will not risk rejecting the null hypothesis. Therefore, sorry, I will accept the null hypothesis and, I will fail to reject the null hypothesis and conclude as the alternative. Sorry for that. In these COVID times, I hope it's not COVID. Anyway, moving on. Now that's the alpha and the p-value. And then you will realize that you talk about confidence levels and confidence intervals. I'm not sure if you go as far as confidence intervals, but if you have an alpha or a significance level of 5%, it means that particular test, you are conducting it at a 95% confidence level. It is just 1 minus alpha. It means you are 95% confident that the results you're getting are correct. So that's basically what a confidence level is. And confidence intervals are generated from confidence levels. Okay, so the first test that we're going to look at is the chi-square test. So, sorry, just a moment. Okay. So for the chi-square test, we're saying that the one that we're interested in is the chi-square test for association. Now, for this particular chi-square test for association, we are saying that it tests association between two categorical variables. Okay, so you find that in books you have different other types of chi-square tests. You have the chi-square test for goodness of fit, chi-square test for homogeneity, but the one that we're interested in here is the chi-square test for association. So for this one, you are testing if two categorical variables are associated with each other, significantly associated with each other. For example, you may want to test if gender is associated with a program that a student enrolls in. Where gender is a categorical variable X, that is 0, this is how it's entered in the package. 0 standing for female and 1 standing for male. On the other hand, you have program, which is a variable Y, where 0 is standing for a program Bachelor of Arts, 1 a program Bachelor of Science, and 2 standing for a program LLB or Bachelor of Laws. And the null hypothesis for a chi-square test is that there is no association between X and Y. Well, the alternative is that there is an association between X and Y. Now, this is how the data would look like in the package, all right? And you find that these are just IDs, and you have gender and program of study, where M1 is a female who is doing a Bachelor of Science, M2 is a male who is doing a Bachelor of Laws, and so on and so forth. And you may have as many sampling units as you want in this particular data set. And we are saying that a chi-square test will test whether gender is significantly associated with with the program of study which a student actually enrolls in. And the null hypothesis is that there is no association. The alternative is that there is an association. Moses will show us how that test is done in R, but when the test is done in R, it is going to generate a p-value from the sample, okay? And for purposes of this particular session, we'll be using a p-value, an alpha of 0.05. So our decision will be based on 0.05. Now, if you conduct the study and you find out that the p-value that you generate is less than 0.05, then it means you are going to reject this null hypothesis. Therefore, there is an association between gender and program of study. A significant association at an alpha of 0.05 between gender and program of study. Okay, I hope that is clear. I will repeat. If you conduct the chi-square test and the p-value is less than 0.05, which is our alpha, then there is an association between gender and study. If the p-value is greater than 0.05, then there is no association between gender and program of study. That is what a chi-square test is going to do. So it is just testing association. This is a chi-square test for association, where variable x is significantly associated with variable y. The next test that we'll look at is the Pearson correlation test. The chi-square test was looking at a relationship between two variables that are both categorical in nature, while the Pearson correlation test is looking at a linear relationship between two variables that are continuous, all right? And an example would be when you want to check if weight is correlated with height, or there is an association, a linear relationship between weight and height. The null hypothesis, just like chi-square, is that there is no correlation between x and y. The alternative hypothesis is that there is a correlation between x and y, where x is weight and y is height. And you'll find that this is how the hypothesis may be defined, that this rho is equal to 0, it means there is no correlation. Or rho is not equal to 0, it means there is a correlation. And you find that in this Pearson correlation test, you plot a scatter plot, which is something that I think you have done, and then you would get a correlation coefficient, which tells you the strength of the relationship. So you find out there is a correlation or there is a relationship, and then the correlation coefficient would tell you the strength of the relationship. How strong is the relationship? So the data structure would look like this. So you have ID, and then you have a variable weight and another variable height. If you want to see if there is a linear relationship between weight and height, and as you can see, both weight and height have been connected. Okay. You will see that both weight and height have been collected on a continuous scale. So what will happen is, when you do the test in a statistical package, the first thing you would want to do is to create a scatter plot. I just took this from the internet, but I'll explain. So assuming we are still looking at weight and height, this scatter plot would have, for example, weight on the y-axis and height on the x-axis. And you will create these scatter plots. And if you look at this particular scatter plot, there is some sort of a trend that you are able to see. The same applies to this second one, but it is not the case for the third one. So if there is no linear relationship between the two variables, the scatter plot will just be all over the place like this. But if there is a relationship, it's either the relationship will look something like this, or it will look something like that. It doesn't have to be perfect as it is appearing here, but you should be able to at least see some sort of a trend when you plot the scatter plot. Now, for the first one, it is a positive correlation. What it means is that as the height values are increasing, the weight values are also increasing. As x is increasing, so is y. So it is a positive correlation. And remember, I talked about the correlation coefficient, it will also be a positive value. And this correlation coefficient takes values from -1 up to +1. okay? If the value is 0, it means there is no correlation. If there is a positive correlation here, like as this one, it means the values will be from 0 to 1. So it will be 0.1 up to 0.99. It can take any values in between there. And the higher the value of the correlation coefficient, the stronger the relationship. For example, this one would have a correlation coefficient of 0.9. It means the strength is 90%. Basically, that's what it means. The same applies to this one. It's a negative correlation. And the correlation coefficient may be the same 0.9, but now negative 0.9 because there's a negative relationship. What this relationship talks about is that as one variable is increasing, the other one is decreasing. So it means as height is increasing, our weight is decreasing, and vice versa. So that is the negative correlation as compared to the positive correlation. Ideally, no correlation should be equal to 0, but you may still get a very small correlation coefficient, maybe 0.07, 0.1. It is very little, or negative 0.05, but the scatter plot is going to look like this. The more perfect the plot, the stronger the correlation. And you find that in packages, you may even plot a line of best fit, and then you will extend to linear regression analysis. But that's what correlation does. It is testing the linear relationship between two variables that are continuous, unlike the chi-square, which is testing for an association between two variables that are categorical in nature. So that is the Pearson correlation. Now, moving forward to our t-tests. T-tests, there are 3 if you remember. So these t-tests are tests for mean. They test for mean. The moment we say mean, we know that we are looking at a continuous variable, because you cannot have a mean for a categorical variable. And I'm sure you were able to do those summaries as well. Those summaries where you are getting mean, mode, median, standard deviation. And a t-test is one that is done on continuous variables, and you're trying to test on do tests on the mean. Now, the first one that we're looking at is this one we have right here, a one sample t-test. So what a one sample t-test does is to test the value of a single mean. And what are you trying to test? You're trying to test if it is equal to a certain specific or specified value. Now you realize that this sample that you are looking at, you have drawn this sample from a particular population. And what you want to test is that, is the mean of that population equal to a certain value, or is it not equal to a certain value? And you go into that population of Malawians, you sample 1 million Malawians, and they are the ones that you're using for this particular test. And we are saying that we may like to test if the average age at school entry is 17. I presume that should be university. So I want to test if the average age in Malawi at school entry is equal to 17. So the null hypothesis is that the mean age at school entry is equal to 17, while the alternative hypothesis is that it is not equal to 17. That's how you are specifying the null hypothesis and the alternative hypothesis for this particular one sample t-test. In books, you find they'll write this with a notation mu. So mu only just stands for population mean, okay? The same as this. So in this case, mu is standing for the mean age at school entry. So we're saying mean age, mu is equal to 17 versus an alternative that mu is not equal to 17. And we have that very same sample of ours, all right? And what will happen is you go in the population, you pick your sample, and then you have the ages collected as it is here. So the first person student at the time they were entering university was 15, another one 24, up to 21, and the sample goes on and on. And just with this information, you can conduct your one sample t-test, okay? You can conduct your one sample t-test, you will do it in R, you see how it's done with a specified value of 17, and then you will get a p-value from that particular test. And if the p-value is less than our alpha of less than our alpha of 0.05, it means you are going to reject the null hypothesis. Okay. And if the p-value is greater than our alpha, then it means you fail to reject the null hypothesis. So that is what you're doing basically in a one sample t-test. It means if you get a p-value that is less than 0.05, then it means you are actually rejecting the null hypothesis, and vice versa. So this is what you're doing in a one sample t-test for the mean, okay? And like I said, you will find out that in books, they'll say this is which is correct. This is a two-tailed test, and it is what is a default in the packages, but there are other one-tailed tests which we're not going to look at. But if you do it in a package, you're basically doing this particular basic test, that the mean age is equal to 17, versus an alternative that the mean age at school entry is not equal to 17. So that's how you conduct a one sample t-test, and this is probably what your data is looking at. I have to stress that it doesn't mean these are the only variables in your data set. Your data set can have so many other variables here. You may have the height, the weight, whatever, but at a point in time, you're only interested in the variable that you would like to get results from. And in this case, it is the age at school entry for a one sample t-test. Moving on to a two-paired t-test. So for a two-paired samples t-test, it is also a t-test. But what this one is doing, it is testing if there is a significant change in a particular variable characteristic at two different measurement times. Okay, so you want to see if there is a significant difference. I would take your attention to this particular data structure. So you find that there is weight before and then there is weight after. Sometimes there is an intervention in between, and you want to see that if that intervention is important, you are going to use a paired samples t-test. In this case, we are assuming that in this sample, there was a school feeding program in between here, okay? So this is the weight of a student before the feeding program, and this is the weight afterwards. And what we want to find out is if the mean difference for this sample is significant or not. If it is significant, then it means probably the school feeding program was important, or it was sufficient, or it did some work. If the difference is not significant, then the school feeding program probably was just not important in as far as gaining weight is concerned. So we are saying we want to test if the average weight of students before and after the school feeding program should be different here. Not is there, but if it is different. And the null hypothesis is that there is a difference in weight before and after the school feeding program, okay? Oh, sorry, this should go out as well. And then the alternative hypothesis is that there is no difference in weight before and after school feeding program. Or from a notation form, you may write that the mean difference before and after school feeding program is equal to 0, versus that it is not equal to 0. If it is not equal to 0, then it means there is some difference. If it is equal to 0, then there is no difference. And this is how your data will look like, and you'll be using these two variables for that particular test. Now, when you conduct the test using these two variables, the values before and the values after, you will get a p-value. Just like we have been doing before, you will use that p-value to make a decision on the hypothesis. So if the p-value is less than 0.05, then it means that the mean difference is not the same. So you realize you're going to reject your null hypothesis, all right? And if it is greater than alpha, then you fail to reject your null hypothesis. Okay. Now, for two independent samples t-tests, you will realize that it's moving from this particular type of data structure. For this data structure, it is the same person, okay? For this data structure, it is the same person, their value before and their value after. The same sampling unit, their value before and their value after, like that, before and after. While in two independent samples t-tests, you will find that it tests if mean for two groups are different. So for this one, you are testing if the mean weight, for example, for females is equal to the mean weight for males. This is an alternative that the mean weight for females is not equal to the mean weight for males. That's an example of this one. And you'll find that For notation, mean female is equal to mean males, mean female is not equal to mean male. And this is how the data will look like. You need these two variables. The variable that is splitting the weight into two categories. So in this case, it is gender. Because how are you going to separate males from females when you are using the variable gender? Where 0 is female, remember our notation, and 1 is males, and you have their weights, okay? So for the two independent samples t-test, what it will do is it will compare the average for males versus the average for females and find out if the mean weight for females in this sample is the same as the mean weight for males in this sample. And this will be done in the package. Everything that I'm saying will be done in the package. It will be illustrated during the session for running this particular test in R. So you'll find out that just as we were doing, if the p-value is less than alpha, you reject the null hypothesis. What it means is that if you get a p-value of 0.04, then you will say that the mean weight for females is different from the mean weight for males. If you get if you get a p-value that is greater than alpha, then you fail to reject the null hypothesis. Then you will say the mean weight for females is actually equal to the mean weight for males. All right. So if the p-value is less than alpha, you reject the null hypothesis. It means there is a difference. If the p-value is greater than alpha, you fail to reject the null hypothesis, and you say that there is no difference. So that is how a two independent samples t-test looks like. Okay, now for analysis of variance or ANOVA, it is an extension of the two independent samples t-test. In the two independent samples t-test, what you're trying to do is you are testing if the mean for group 1, females, is the same as the mean for group 2. In ANOVA, on the other hand, you're trying to test if there is a difference in mean when there are more than 2 groups. So it could be 3 groups, 4 groups, 5 groups, 6 groups, and so on and so forth. And in our case, we are getting the very same example of programs, okay? So remember we had 3 different programs: Bachelor of Arts, Bachelor of Science, and Bachelor of Laws, okay? So what we want to test is, we want to test if average final scores are the same for students enrolled into the 3 programs, or if they are different, okay? So the null hypothesis is that the mean score for Bachelor of Arts is equal to the mean score for Bachelor of Science, is equal to the mean score for Bachelor of Laws. The alternative, not quite, this is not how it's supposed to look like, but the alternative is not, keep that in mind when you're going through, is not specified like this. The alternative would be that at least one of these is different. So at least one mean is different. As long as one mean is different, then that's fine. Not mean 1 is not equal to mean 2 like that. No, I think, yeah, it's not. Let's just say that it's not like that. So take note of that correction. So we are saying the null hypothesis is that all the mean scores for the 3 programs are the same. The alternative is that even if just one, at least, yeah, so at least starting from 1, just one not being equal to the others, then you're going to reject the null hypothesis. Then you will say that at least there is one that is different. It could be all of them are different from each other, or just one is different. So you go on to specify the alternative hypothesis that way. Now, the data structure for ANOVA, this is how it looks like. This is our ID, just like I've been doing before. Okay. Okay. So I think that the table that I have here is not the correct one. But the table that you would actually have is the one that has variable here, education program that a student is enrolled in. Okay. So we may just go back and use this one, this particular table. Sorry. No. Okay, let's just use the very same one. So we can have the mean score here 56, mean score 67, mean score 78, mean score 69, and mean score 40%. So you have these as scores, okay? So you have a program of study versus a score. Now, what you are basically saying is that, okay, that's better. We should have it here. Yeah. So what you're saying is that you have students that have been enrolled into the 3 different programs, and then each student will have a score. And you want to test if the mean score for program 0, which is Bachelor of Arts, is the same as the mean score for program 1, which is BSc, the same as the mean score for program number 2, which is Bachelor of Laws. And you are doing an analysis of variance test on this particular sample. If you get a p-value that is less than alpha, it means you actually now reject the null hypothesis. So if the p-value is less than alpha, it means that the mean scores for the 3 programs are not the same. Then there is at least one that is different. If the p-value is greater than alpha, it means you are going to fail to reject the null hypothesis and conclude that the mean for Bachelor of Arts is equal to the mean for Bachelor of Science, is equal to the mean score for Bachelor of Laws. And that's what you're basically doing in analysis of variance test. And for today's lesson, this is where we stop. But after you conduct an analysis of variance and you end up rejecting a null hypothesis, and you say that at least one mean is different, so you say at least one mean is different. Then you can go ahead and find out which one is different, which means are different. And that probably, if there is need, it can be a study for the next, maybe another session in the future. But basically, this is what you are doing in analysis of variance test, which is a test for means for more than 2 groups. And you want to see if there is a group that has a different average. Yeah, so this is what I had for you guys today. I'm not sure if there are any questions.
Thank you so much for the presentation. Yay, guys, we can ask questions to the presentation. I only know the technical part of it. So, like, as I said in the subsequent lessons, I think some of them we already covered, like in the previous lessons, but still more, we will just, because we have all the basics now, then we can do the coding in R and how it comes out, and do the interpretation quite well compared to maybe the previous lesson that we offered. So feel free to ask questions.
Okay, it seems like there are no questions, which is, I assume is a good thing.
Hello?
Hello, it seems like there are no questions. Is there someone who has a question? Leonard, you want to ask something?
Yeah, I just want to ask on the t-test, like I've
Yes.
understood all the descriptions, but there are conditions when you can say I'm going to use one sample pair test, or here I'm going to use independent. In terms of the population, are there other conditions which you need to consider?
Yeah, okay. So I'm not sure if I'm getting what you're asking right, but I'll try to answer the way that I've gotten it, and you tell me if that's what you were asking. So, like I said, remember I said these are parametric tests, is it? And for parametric tests, they have to follow a certain particular distribution. So for these t-tests specifically, the data must follow a normal distribution. So you would have to do a test for normality to find out if the data is distributed as normal. That's the first thing. So if the data is distributed as normal, you can go ahead and do these particular t-tests. Otherwise, if the data is following another distribution that is not normal, the rule of thumb is that the central, we use a theorem that says when your sample size is large, then you can go ahead and use a t-test because the population is going to now start going towards the normal distribution. So large sample starts from 30. In most of the times, if you're doing studies, you have samples larger than 30. But if you have samples smaller than 30, it is advised that you also do the non-parametric equivalence. So that is an important thing that you need to keep in mind, that the data must follow a normal distribution, or it should follow any other distribution but large enough. Now, how you choose which one between the three you want to use depends on the question you are trying to answer. For example, in one sample t-test, you will realize that the question you're trying to answer is just based on one variable, as you can see here, for example, age. So if what you're looking at is just to find out, for example, if, for this particular example, if age at school entry is equal to a specific value, then automatically, you're looking at one sample t-test. You just want to test one variable for that particular sample. So that would direct what you want to use. It could be something else. You may want to find out, I understand you're using data on cars. You may want to find out the mileage per hour, the average mileage per hour for the cars that are in your sample. It means if you are saying, okay, you are hypothesizing that all the cars have an average mileage, for example, of 100 kilometers per hour, okay, speed rather, 100 kilometers per hour, then it means you're going to use a sample t-test that will be testing an our hypothesis that the average speed for these cars in this sample is 100. This is an alternative that the average speed is not equal to 100. So depending on the question you're answering, it is what will help you determine whether you use a one sample, an independent samples, or a dependent samples t-test. The same goes to paired. If you're trying to check the difference between they will look like two variables as they are here, but you realize that both of them are coming from one particular sampling unit, okay? So X1 and X21 are coming from one particular sampling unit, and you want to see across if there is a significant difference. And like I said, most of the times there is an intervention in between. You collect information from the same sampling units before and the same sampling units after, okay? So you may have something like, if you're looking at the cars sample, you may be looking at the thing, something like fuel consumption before and after service. So you have car number 1 with fuel consumption now, car number 2 now, up to car number 5 now, and you take all the cars to service, and then you take their fuel consumption after that. And then that you should be able to find out if the service is actually doing anything to the fuel consumption, if there is a change in the fuel consumption because of the service. So you see that now it's also the question that is helping you decide whether you're using paired samples. While in independent samples, the question basically is to look at differences between two mutually exclusive groups. Okay, so the two groups that we're talking about here are mutually exclusive. You cannot be female and male at the same time. Okay, so you have one group in one category, the other group in another category. So here you may be looking at, you want to find out the same question of fuel consumption, but if cars made in Germany have the same fuel consumption as cars made in Japan. Okay, so you would have cars Germany, Japan, Germany with the fuel consumption, and there are two independent groups. A car is not made in Japan and at the same time made in Germany. It's either it's from Germany or it's from Japan. So the question that you are answering is what actually helps you determine what type of analysis you will use. I always say that if you're doing analysis, run it with a friend probably who is a statistician, or even you yourself may be a statistician and you're not even sure about it. But you may ask them, I want to use this test, do you think is appropriate? And then you can get advice. I hope that answers you, Leonard.
Yeah, it's answered. Thank you.
Okay, thank you. Okay.
All right.
Robert,
So, yeah, if there is no any other question, first of all, I would like to thank you so much for your presentation. I think it's something that we appreciate now, and even for those that will download the material, I think they will go through it and learn new things. For some of the people maybe who did some statistics way back, I think it's a quite good reminder. I choose to believe that for those that are working in developmental organizations like this NGO, we don't do this kind of test and the like. So most of the times once you just collect data and then do only basics, I think all these usually go. And so this has been even an opening eye to me as well. I mean, I enjoyed the lesson, and what I would say is, on behalf of all the team that have been getting the trainings, I think we will still need you at some point. But for the meantime, thank you so much, and enjoy, and be safe, everyone, from COVID, so that at least we be strong and keep the sessions going on. Unless if there are any words from the group, just this is your time, as we're remaining with 2 minutes.
Nothing, I think we can close.
I think everyone is afraid of saying something. So yeah,
That's okay.
I think we can close.
Okay.
All right.
Bye, guys.
All right, bye. Thank you.
Thank you.